Hi, Calculus. I am Mrs. Gogarty, one of the AB Calc teachers, and welcome to our next lesson within our first unit. So today you will need the 2.6 notes sheet on continuity. So once you find that, it should look very similar to the screen that you're seeing right now. You, by all means, should take a look at this limit problem and see exactly how you're doing with that. Okay, that's going to be a review from things that we've looked at in the past. And what I want you to do to start off is to just take a moment and read over what is on this page. Okay, there are a lot of really good notes right from the beginning explaining what is continuity, and better yet, what is not going to be a continuous function. Okay, so pause the video, take a moment, and read over it. Okay. So coming back to me, you should have wrote over this nice little paragraph here. And there's just some key things that I want to make sure that we understand. Since math is such a foreign language, sometimes we can read these words and we want to make sure that we understand what the symbols are that we're taking a look at. So the first thing that I want to take a look at truly is going to be what is a continuous function. Okay, so if we want to talk about continuity at any given point, these are the three things that must exist for that to occur, for continuity to occur. So let's look at what does it mean for f of c to be defined? Okay, well, just in the easiest terms possible, there has to be a point. So if we're looking at a graph, there has to be a point at some x value, we're calling it c. So in other words, there can't be any holes, there can't be any gaps, there can't be any asymptotes. So as long as we have a point, we can say that the function is continuous at that value, okay? So now let's take a look at the second one though. The limit as x approaches c of f of x exists. Well, what the heck does that mean? Well, we've been talking about limits quite a bit in the last few sections. Mr. Leavenworth and Ms. Jarosik have talked about those in different videos, depending on the videos you've seen. And what we're looking at here is that the limit from the left of C is equal to the limit from the right of C. So as we start considering our left hand and right hand limits, I'm looking at the fact that as we approach the limit from the right and the left side, whatever the value is that we're looking at, the limit's the same thing, okay? And so then lastly, our third thing that we've got going on, the limit as x approaches c of f of x is f of c. So what does that mean? Well, that means we have a unique value, okay? So it's easier kind of to show you in a picture. Let's consider this. Like, let's say that my input is c here. Well, then the limit as we approach x, or we approach c from both sides, we're getting a unique point. So imagine that I'm just going to make some random graph coming through here. Well, the limit as we approach from the left, okay, so imagine walking along from the left is going to be the same thing as if we're walking from the right. We get a unique output of f of c. Okay, so now let's kind of continue on down here. Well, then if these three conditions have to be met for there to be continuity, well, if they're not, then we have discontinuity. So I'm going to look now at my three different situations that would show that we do not have a continuous function. So in general, what is this talking about? Well, let's go back to looking at f of c is not defined. Well, in our past classes, Algebra 2, Pre-Calc, and so forth, if f of c is not defined, I want you to think about how does that show up on a graph? If we don't actually have a defined output, what are the options that we have for that? And those come and show up as holes. They can show up also as asymptotes, okay? Specifically vertical asymptotes when we're thinking there, all right? So next, part 2 here, the limit does not exist. Okay, well, if we just kind of think about what we were writing up here, that in order for the limit to exist, the limit from the left has to equal the limit from the right. Well, then basically the limit as x approaches c from the left is not going to equal the limit as x approaches c from the right, okay? And we've seen some graphs of these even. So I'm just trying to think of something nice and easy for us. If we had just a general graph, okay? What if I looked at a function that did this? Now I'm just making that up. This is a function, it's gonna pass the vertical line test, but the limit from the left, if we started looking at what are we approaching, so walking along here, we're gonna get a different output than if I was coming along here. So my limit does not exist. There's a discontinuity of a gap going on in this picture, okay? And then lastly, part 3 here, if I'm looking at this option, if I consider a graph really quick, well, this is telling me that the limit does not actually equal f of c. So let's see what I mean by that. So if this is my input c, okay, I am going to consider a graph where, all right, what about something like this? Okay, now this is just an example, but f of c is defined up here at this ordered pair. Okay, so if I could kind of take a look at, I'm just trying to pick a color really quick, that here's the definition of f of c, here's my output, but that output does not equal the limit that's going on along here, okay? So here's just some quick little ideas of what's happening, of how can we tell that we don't have a continuous function. Now, honestly, the biggest thing I remember in pre-calc and even in algebra 2 talking about, if you have a picture where you have to pick up your pen or pencil in order to draw it, then that means you probably have a discontinuity somewhere. So in number 1, if I come back to this, in number 1, okay, anytime there's a hole or an asymptote, well, then I'm gonna have to pick up my pencil or pen while I'm drawing the function. There's gonna be a hole or potentially a gap or an asymptote that is preventing us from being able to draw the entire picture. In number 2 here, if I'm looking at this, I drew a hole and I drew a gap. So this area that I'm gonna circle here, this is where I'm having a discontinuity, okay? In number 3, really quickly, well, once again, can I draw the entire graph without picking up my pen? No, here is my point of discontinuity, okay? So keeping that in mind, let's take a look now as we go down to this next set of examples. And by the way, I use the term gap, but clearly we can see in our notes here even that the word jump can be used as well, okay? So example 1, use the graph to determine the limit and discuss the continuity of the function. Okay, here's the cool thing. You've seen these graphs before. They showed up, sorry about that. They showed up when we were looking at the 2.1 to 2.3 notes. So you have a little bit of experience with these. So let's take a look what's happening, or actually I would encourage you, pause the video, answer the limit questions for the 4 problems. Okay, that's pretty much acting as a review at this point. So pause, answer the limits, come back to me. I'm gonna write the answers in and we'll see how you did, okay? All right, so when you came back, how did you do? So if I'm looking at the limit as we're approaching -1, we're gonna again remember that we are not evaluating a limit by the actual function. Like, I don't care what's happening at the point, I care about what's happening around the point. So if I take a look at this first one, I'm not worried that the limit at, or that x of at -1 doesn't exist. So f of -1 is a hole. That's okay. But what I'm looking at as we walk along this line here, walk from the left and from the right, what are the outputs getting closer to? And that's 3, okay? Now, bigger question here is, do we have a discontinuity? And we for sure have a discontinuity. We have a hole. So this function is discontinuous at x equals -1. Now, I want you to challenge yourself though further of, okay, if it's discontinuous at x equals -1, which of the three conditions did it fail? What did f of x fail? So we have a hole. So what does that mean ultimately? The limit still existed, okay? So I'm looking at the fact that really what's happening is that f of -1 is not defined. Okay, so if f of -1 is not defined, that is why we have discontinuity or a discontinuous function. So finally, what I want us to look at is that our function is then continuous on the interval -∞ to -1, and then from -1 to infinity. So it's continuous everywhere, just not at -1. We have to exclude -1 from the answer. Okay. All right, let's move on to number 2. Ask yourself, can you graph that entire function without ever picking up your pen or pencil? And I would say yes, you can. There's no holes, there's no asymptotes, there's no jumps or gaps. So this function is continuous, and it's continuous everywhere. So it's continuous over the interval -∞ to infinity. All right, let's take a look at the next one. Okay, when I look at this next one, could you graph the entire function without picking up your pen or pencil? Okay, no way. I've got 2 problems going on with this one. I've got a hole and I have an asymptote. So this function is definitely discontinuous. Okay, but it is discontinuous at 2 points, at x equals 2 and at x equals 3. But their reason for their discontinuity is different. So I want you to challenge yourself for a second. How could you write that we are like, sorry, let me rephrase this. How can we say that it's discontinuous at x equals 2? Like, what's the reason for it? Okay, what's our reason for the discontinuity at x is 3? So x equals 3 to me is a little bit easier because that's just like our very first one. So f of 3, whoops. Sorry, my pen decided to stop working there for a second. F of 3 is not defined. That's the reason we have discontinuity at 3. But what would be the reason that we have discontinuity at 2? Okay, so if I come back and I look at these options, okay, it's not that it was undefined there, but it's a little bit more than that. Does the limit exist? And I'm going to go with the fact that, okay, well, if our graph is approaching 2 from the left, how is that different from the output of 2 to the right? So I'm going to go back with the fact that our limit doesn't exist. So not only is f of 2 not defined, okay, because that's important too, but in addition, the limit doesn't exist. So I'm going to say here the limit as x approaches 2 of f of x does not exist. All right. And to finish this off, I'm going to say my function is continuous on the interval -∞ to 2, 2 to 3, and 3 to infinity. Okay, so I have to write each of those intervals because I need to exclude 2 and I need to exclude 3 from the continuity. All right. Okay, I'd like you all to try number 4 on your own, okay? And then definitely that's something that if you're not sure how to do it, check the answer key that's gonna be posted, and then also let your teacher know, all right? Okay, so I wanna move to the back page after that. All right, so this is kind of more of the same type of questions, and I just wanna take a look at it in the terms of, hey, you don't always have to graph these out to figure out where something may be discontinuous, okay? Now, here's where we have to draw back on our knowledge of all the things we learned in Algebra 1, Algebra 2, and Pre-Calc. All of those functions you spent time with, okay? And the first thing I want you to ask yourself is, let's look at that A. What kind of function is A? And I'm hoping that you can quickly tell yourself like, oh, I see an x squared. Okay, well, if it's an x squared, then that means that I have a function that is a quadratic. Well, I don't need to graph a quadratic to know, are there gonna be any place, or is there any value that's gonna make a quadratic undefined? So I'm thinking right now about the domain. What have you learned about a quadratic's domain? And that should be that it's all real numbers, that there's no point where this function could be discontinuous because we're gonna draw a parabola. And I don't care where the parabola is at on the graph, I know it's gonna be continuous. So save yourself some time and just stop and think for a moment about what type of function are you working with. So this is continuous over the interval negative infinity to infinity. Okay, so I'm really starting to think about the domain. All right, now compare that then to B. If I'm looking at B and I have x plus 3 over x squared plus 3x, okay, I'm going to think back. Think. What kind of function is this? Okay, it's not as basic as a quadratic or a linear. We've got this division symbol in the middle, right? So this was a rational function. We're seeing those a lot, okay? So if this is a rational function, is the domain going to be all real numbers? Or are we going to have some places where maybe we have some discontinuity because there might be some holes or a gap or an asymptote of some sort? And if you remember about rationals, they had holes and vertical asymptotes, horizontal asymptotes, all that good stuff. So in order to figure that out, I'm going to need to look a little further at this graph. Or I'm sorry, not the graph yet, but the equation. And when I see this, oh, my x plus 3s are going to cancel. That should tell you something. What's happening at x plus 3? And that is that we get a hole at x equals negative 3. That also means that this x value right here is a vertical asymptote, okay? So I don't need to know a ton about what's going on in this graph, but just knowing those details, I know that, okay, if I put my vertical asymptote on here, I definitely have a discontinuity. And then if I just consider that somewhere on this graph, okay, I'm just making this up right now, somewhere at negative 3, I can actually plug that in and figure it out. We're gonna have a hole. Then I know I have 2 points of discontinuity. So if I needed to make a conclusion about this graph right now, I know that we have a discontinuous function at x equals 0 and at x equals negative 3. Okay, so now I could go back to my rules and say, well, all right, if I have a hole at negative 3, then I know that it's failing the first test of f of negative 3 is not defined. There's no value. And then I know that because there's an asymptote, I know that the limit most likely is not going to exist. Okay, so more than that, I can make a conclusion now that that function has to be continuous from negative infinity to negative 3, then from negative 3 to 0, and then from 0 to infinity. And I apologize, I forgot to put my union symbol in here. Okay. All right, so I'm gonna leave you with the last one to try on your own. We have a piecewise function. So piecewise functions, we've got to make sure that these values, when you look around 2, we need to make sure that we know the output of what's coming out of both of these equations. If they're not the same thing that's coming out, then we might have a jump or a gap, okay? All right, so other than that, I think at this point, you guys should be at a comfortable enough that you can try C on your own, and then you can also try the intervals of which this additional rational function, figure out where it's continuous. So this equation or this function right here is very similar to the example that we just went over. Okay, so I want you to try that. All right. Now, lastly, there's just some notes on this page that could be beneficial for you to look over. Definition of a vertical asymptote. Basically, we can already see in the examples that we've been given that the limit from the right of an asymptote is going to be going up to infinity or negative infinity. And the limit from the left could also be doing the same thing. So I want to just scroll back. We saw that, okay? Here in example 3, we had a vertical asymptote that we could see in general because the limit of the function from the left is going to negative infinity. The limit of the function from the right is going to positive infinity. Now, even if those would have gone in the same direction, we could still conclude that we'd have a vertical asymptote, okay? Meaning, just one last thing, okay? If I took a look at a graph and I drew in something like this, okay? And I'm gonna call this value here A, all right? Well, we can conclude that we have a vertical asymptote because of these definitions over here. So the limit as x approaches A from the right, so this one is talking about from the right. If you notice, as we're approaching A from the right, our function is up here at infinity, okay? Now, at the same time, if I'm looking at approaching from the left, I still have my function is coming up here at infinity. So even if we didn't have both of those, we could still make the conclusion that what has to be happening here is that we have to have a vertical asymptote, okay? So one last thing to remember, and this is a huge concept that really kind of messes with people over time. Infinity is not a number. It's a concept of numbers getting larger and larger and larger and larger. So I don't want anybody to forget that infinity is not a distinct value. So therefore, it fails as a limit. However, by saying that a function goes to infinity, we're describing its end behaviors, or one of the end behaviors. We're describing what the function is doing. So basically, it's just an important thing for you to remember that's listed here. It seems confusing, but overall, just keep in mind that infinity is not a specific value, but it does describe where the graph is going. So therefore, we can talk about a limit going to infinity because it's giving us information. Remember, math is about communicating something to you. So if you know that a limit's going to infinity, then you know that the arrows or these end behaviors right here that I'm looking at, they have to be going up, okay? Vice versa if I said it's going to negative infinity, okay? So what I would like you to do next before you watch the next video is on the 2.6 notes sheet for intermediate value theorem, there are 4 examples on there also of continuity, and specifically trying to describe like where does the discontinuity, or where did the continuity fail? Like, so in other words, describe the condition of continuity that didn't work. So you're going to be looking at the very next note sheet, and we're going to pick up there when we come back. All right. So I hope you're all having a great day. Thanks for watching,